are you guys doing? Welcome to Eureka. I am Kevin Whittinghill.
And my name is Alan Saakyan.
And we're the hosts for the show. Are you guys prepared to get your minds blown?
Yeah.
Yeah. This is going to be definitely a mind-blowing Eureka show.
Yes, it is.
We're talking about nuclear fusion. Anyone here an expert on nuclear fusion? Okay.
We
Nobody.
have an expert.
Oh, you have one expert? Okay, we'll find out. We'll see if you are an expert. If you don't know much about Eureka, we have a guest scientist give a fascinating talk. We have comedians up on stage. The scientist will ask you guys questions, and if you get it right or close to right or good enough, you get a great prize in our little Eureka box back there. So it's fun. We want everyone to be engaged. You feel free to ask questions. It's all about just having a fun time learning about, in this case, nuclear fusion and getting some laughs.
Yes.
All right.
Yes. Yes, our mission in this, I always like to say our mission is to demystify science in ways that are relatable, educational, and entertaining. So please do bring friends and enjoy science comedy.
Yeah. So let's do this. Let's start this puppy. You ready?
Yeah, let's do it.
All right. We're going to start by introducing our comedians. Why don't you come out? Katie Rubin and Matt Gubser.
Woo!
Come on down. Yes. Have a seat at the table. Now, these are the best faces I could find for you guys. Matt, every photo of you just looks sexy and suave. And Katie, I don't know, maybe you sat on a grape. I don't know what was happening. But it's a nice, silly photo. How are you guys doing?
Good. Are these for us?
Those are for you guys.
I got 2 waters.
Oh, well, I was actually going to borrow that
Nope, those
at
are
some
both
point
mine.
myself. You can have it. Good to know.
I drank out of all 3 of them.
Oh, you did? Okay. Good to know. Do you guys know much about nuclear fusion?
No.
Okay.
I have an associate's degree in nuclear fusion.
Oh, you do?
That's,
Oh, sweet.
What were your studies about?
What's that?
What were the studies about in the subject?
Nuclear fusion, dumbass.
Yeah.
Like, what did,
That's what the community college told me. That's great. So yeah, you're obviously an expert. We got that.
I have something like nuclear fusion happening here and in my loins just because of the handsomeness that's happening here.
Oh, watch out. Woo! She does need 2
Right
glasses
here.
of cold water. This is getting a little... Okay. I'm glad you guys have met the comics. They've met you. They're meeting each other right now. It's getting hot under here under the lights. Shall we
Yes, let's introduce
the
our
man of honor?
scientist.
Yes.
So our scientist is Dr. Lorin Benedict. He is a physicist at Lawrence Livermore National Laboratory. Yeah, there he is. Come on out,
Lauren.
Come on
Don't
out,
be
Lorin.
afraid.
Woo! And yes, this is a very long list of accomplishments. We have, you've studied topics ranging from nanoscience to magnetism to nuclear fusion. Primary interest in predicting the properties of matter at extreme pressures and temperatures. What happens to matter when it gets really, really
That's
hot?
yours, yeah. We wish to know.
Yes.
So yeah, we have also placed you right here in this, I guess, nuclear fusion reactor, because you're the center. It's going to get hot. So we're going to start. I guess you're going to tell us a little bit about yourself. That's probably the best place to start.
Yeah, I can do that. Well,
Yeah, you know something about yourself?
a little bit.
Okay, good.
Yeah,
Sounds
I mean, so
excellent.
let me just mention. Oh, what am I doing? I have a microphone.
You have a microphone.
I think that the first thing that I want to communicate to you all is that I'm not really much of an expert in nuclear fusion, despite what these people are saying. I mean, my expertise is this sort of matter in extreme conditions, but the kind of fusion that we're trying to affect at Lawrence Livermore Lab, as I'll show you, is one in which you have to put the matter in very, very high pressures and temperatures in order for the stuff to fuse. And my expertise is more in the properties of matter when it's confined to very small spaces and when it's very hot. So the actual fusion itself is something that, although that's the point, it's actually something that I know embarrassingly little about. So feel free to ask me lots of questions that I will probably fail to answer.
I guess we'll have Matt then be the expert on nuclear fusion.
Yeah.
Associate's degree. Yes.
Associate.
thank you for explaining that distinction that no one in this room understands. That's-
All right, let's start right off with this is my favorite slide he presented to us. Can everyone see it? Am I in the way? I'm in the way. Okay.
Not by much, just the head.
You could see right here. This is where you work, right?
Yeah. So this is Lawrence Livermore National Laboratory. A lot of people mistake it for Lawrence Berkeley Laboratory. It's the same Lawrence. It was named after Ernest Orlando Lawrence, who's the guy who invented the cyclotron or the atom smasher. This, unlike the Berkeley equivalent, is located in Livermore, which is why it's called Lawrence Livermore. And Livermore is sort of halfway between here and the Central Valley of California, so it's about 50 miles east of here. This used to be the site of a naval air station during World War II. It is literally a square mile each, so you can see the boundaries of the thing. Let's see. You can see very good. Thank you, boundary man.
Useful for something.
So this is, it's literally a square mile. The hills that you see in the back are the hills that separate the nominal East Bay from the so-called Tri-Valley, which is where Livermore and Dublin and Pleasanton are.
This is very detailed.
And that's my office. So it's in the southwest corner of the laboratory. And this thing is what we're going to be talking about, which is called NIF, which is the National Ignition Facility, and that's in the opposing corner.
Wow, I like how you break it down as if we wanted to stalk you. We know you're like walking route to the NIF.
Where's the cafeteria?
There are two. Thank you for asking. There are two cafeterias. Cafeteriae.
This is half our show, by the way.
Do they have lockers
The
that they
first
can
one is
still stuff
here.
you into for saying cafeteria?
Yeah. The first one is here.
God.
The second one is there, near Lake Hausman. I don't know who in the hell Hausman was, and this is more of a pond than a lake, but it's literally called Lake Hausman. So, yeah, there are two cafeteriae.
You're getting so much information here you didn't know. Like, forget the nuclear fusion. Where are the biscuits?
Where's the best parking?
Well, that's a very loaded question. It's probably near where I am, because, well, I'll get to that later. But the parking around this, it's very sketchy. There are places where you have to park quite far away from where you work. If you happen to work, let's say, over here, so it's a source of constant frustration.
Well, this feels like a passive-aggressive slide. Like, I am here, and look what I'm forced to have to walk to.
No. Good question. Because the thing is that almost nobody that I know actually works there. The people who work there have to be in these clean suits and everything, and I'll show you. I don't think I'll show you any pictures of them, but you'll see why that's the case. Everything has to be nice and spick and span, and so, the scientists that I know mostly are not even allowed in there. The people that are sort of designing the experiments and analyzing their results and theorizing about what happens are in all these other buildings. Wow. The stuff happens there, but those people are the technicians who, and all of us have toured this facility. I'm sorry.
No, the technicians are the ones who have associate's degrees.
Yes,
Yeah,
but they're also the most useful.
What exactly are they working on in that building?
We're going to learn all about
learn
that.
that.
Katie
All right.
Rubin.
We're gonna
Take
move
it there.
to
Take it home.
We're going to move to the science section of this talk.
I'd like to hear more about parking.
Well,
Yeah.
we can do that. So the
Science
first,
parking.
here's the first question, and I'm hoping that this is a fairly easy one. This is the one that you all, if you answer it, or whoever answers it first. I can't see any one of you because of this weird light thing, but somebody will adjudicate.
Yeah.
This is if you get the answer, then you get some kind of a prize, right?
Yeah, we explained that. You're doing a lot. You're doing very good at explaining.
Okay.
I'm just saying.
What is nuclear fusion?
What is it? Oh.
Yes. Hold on.
Two atoms combine, or the two atoms combine to form a single, or I guess not necessarily a single, but a lot of energy and the new element.
I think that wins.
That's correct?
Yeah.
That's Eureka.
That's a Eureka! Woo!
All right, my comedians, what do you think this very intelligent man should win? That's the first question. Yeah?
Definitely the white fluffy thing.
Okay, that is the mad scientist wig. Huh? Yeah, why don't you put it on him? Let's see how he looks. Look at this guy. Oh, there it is.
Woo!
Big round of applause for our mad scientist. And you're in the Tenderloins, you can wear it outside.
You look like a young Bernie Sanders.
All right, we'll just keep moving.
Yeah. So, as you correctly stated, it's when two elements, in particular two nuclei of smaller size, come together and form a bigger nucleus. And as also you correctly pointed out, that often is accompanied by a release of a large amount of energy. So the particular fusion reaction that NIF is trying to affect is the one in which two forms of heavy hydrogen, deuterium and tritium, so deuterium is, so regular hydrogen is what? What's regular hydrogen? Okay. What is it made of? Right, okay, proton and electron. So this is, a deuterium is a proton and a neutron in the nucleus, and since a neutron weighs about the same amount as a proton, that weighs twice as much as a regular hydrogen atom, but it still has the same charge as a hydrogen because a neutron, is neutral, so that it just has one electron orbiting around it in its neutral state. So when a deuterium guy and a tritium, which is one proton and two neutrons, that's 3 times heavier than a normal hydrogen, come together, then they would form a helium nucleus plus an outgoing neutron, which has many millions of electron volts of energy. We can talk about an electron volt later, maybe, and that's this very energetic fusion reaction. So the inputs are 2 heavy hydrogens, and the output is helium, and a hell of a lot of energy for this neutron coming out. Okay.
Hopefully we can use that energy to power civilization.
Yeah, that's the whole point of this, or one of the main points of this, which is why it's been studied for a long time. Although I will also, go to the punchline, and that is that although we have certainly succeeded over many years in doing this kind of in miniature, this, we can only use it as a power plant if you get more energy out than you put in to make this happen in the first place. And we haven't succeeded in doing that, and people have tried to do that for over 50 years. So that's where that stands.
We need funding.
All right.
So this
Back
is
to
this
the buildings
yeah.
again. All
So
right.
More buildings.
Cafeteria again.
Cafeteria.
That is nice parking.
Yeah, right. If you work over there, you're the parking king. I mean, but again, this is where the
Do
technicians
you guys
are.
use segways?
No, but you know what? Let me just say something about that. Lawrence Livermore Lab is particularly hip because throughout the square mile, they have these cute little orange bikes. And they don't belong to any one individual who works there. They're just littered throughout the place. And so if I'm going from one building to another, I can just pick up a bike from one place, drive the bike, drop it off, and then walk back or whatever. They're ownerless bicycles that are owned by the collective. So that's kind of hip.
Do you have to be a socialist to work there?
No. Good question.
Maybe it helps, though. I think
Shared economy.
I'd probably
Good job.
take the bike.
That's right. So that's the building, and basically, I'll show you a little bit of the insides of it in picture form. But this is a very large laser. It's actually the world's largest laser facility. I mean, it's literally the most powerful laser in the world by a country mile.
What kind of a laser is it?
Well, there's many different kinds in there. So it starts with very low-powered, I think, ytterbium-dosed glass or something, and that produces infrared light that then gets amplified again and again by xenon flash lamps and a bunch of other stuff that, frankly, I don't understand because that's, again, not in my area of expertise, sadly. But all that's packed into here, and it has to be long because lasers, what is laser? Does anybody know what laser stands for? What's it stand for? Wow,
Whoa.
man, this is some smart.
Smells like graduate school in
Let's
here.
hear that. Let's hear that again.
Light amplification of through stimulated emission of radiation.
That's exactly right. Very good.
Took it out of my mouth. That's
Can we give a
a
Eureka
round
for
of
that?
applause.
And that wasn't even one of the questions, so you are prizeless, buddy. But the reason this has to be so long is the amplification part, because basically the light has to pass back and forth through various media in order to continue to stimulate the matter, to excite electrons so that when they fall down in their energy levels, they emit more light, and they tell two friends, and they tell two friends, etc. And that has to happen so many times. That's why this thing is so long, and any given beam of light traverses this even many, many times.
So if we don't actually figure out nuclear fusion, can we just turn this into a death ray? Is that like the next?
Funny you should ask, because actually this very building has been used in, I think, one of the more recent Star Trek movies, the interior of this building, when they weren't actually shooting the stuff. So Hollywood has already used the interior of it.
Are we going to see some of that next?
No.
Okay. That's the one exciting.
What do you think, I'm a dork?
I don't know.
Okay.
Well, I think I think you're a dork. Let's take.
Okay.
I'm
So
kidding.
this is the inside of this laser bay, and this is it's actually, I said it's the most powerful laser, but it's actually 192 independent beams, okay? And this is the 192 of them. You can't see some of them because they're below other ones, okay, that you can see. And this thing is, I think, 3 football fields in area and several stories high. So it's really, it's an enormous laser, okay? So the point of it is that, and I'll show you an interior of this in a minute, but there's this big spherical chamber that has a bunch of holes in it where each one of the 192 beams goes through, and then all those beams are focused to the very center of the chamber into this little thing. And what this is a gold canister. It's a canister made of gold, where what the beams do, this is an artist's rendition of the beams, they hit the interior of the wall here, and they make the thing very hot, and then that gold, because it gets so hot, radiates X-rays into this little chamber, and the chamber is very small. I'll show you how big it is, compared to like a human hand in a minute. Inside that chamber is a little pellet the size of a pea, and that's the stuff that has deuterium and tritium in it. And when the X-rays impinge upon this little thing, okay, which is like a baked Alaskan of deuterium and tritium inside, and something, holding it in the inside, then it heats this outer stuff up, making the other stuff go inward like that, like a spherical rocket, right? Stuff comes out this way and the thing goes that way. So that happens in all directions, making the thing crunch in on itself, and that's what creates the fusion. So that's how NIF is supposed to work.
And that entire process takes billionths of a second, right?
Right.
Okay,
You all
Lauren,
get that?
I'm just wondering, Lauren, can you be a little more specific? No?
Hey, this is how I roll, you know what I mean?
Does anyone have any questions thus far? Oh, just taking it in.
I have a
get
question. I have another question.
Okay.
Have any of the people in any of the buildings that we've seen had any sex with any other people ever?
I think so.
That's a different type of fusion.
So. Yeah, that's a different type of fusion.
Okay.
That's this. I think that you guys did a show on that though a few shows
We
ago.
did. We
right?
did a human sexuality.
Well, we talked
show.
about it a moment ago.
Oh yeah. All right. You're trying to get back to
Yeah,
the sexy
I'm
Jesus.
just bringing
I
it
got
full. Okay. Thank you.
Gotcha.
Let's have our audience
Yeah.
question.
So, what part of the baked Alaskan is the meringue? Exactly.
Okay, we'll get to that on the next slide.
Okay. And
Oh, very good.
is your office as far away from everything else as possible for a reason?
No, it's not. It's really just kind of accident.
He's the real
Seniority.
mad scientist.
Yeah.
So what do we have here? Look.
Okay.
Dang,
thi-
that's small.
This is that gold canister, and you can see how ridiculously small it is. That's not a person who has elephantiasis of the hand. That's actually it's okay. And then
That's funny.
So since you measure the theoretical properties of if whether or not it's supposed to be small or big, why is it not large? Why is the canister not large and the P is not larger
yeah.
or smaller for that matter?
Well, so I'm not actually going to be able to answer that question completely because I don't know all the answers. But let's just say that there are so many trade-offs in designing this thing that this is sort of the optimal size given the power of the laser that they have. I can't say it any differently than that. I mean, and if you make it too big or too small, the thing just isn't going to work with this laser that we have well enough. And it's like a 50-year history in figuring that out. It's in the engineering design of this. I wish I had a better answer. And if I was one of the people who designed it, I probably would have an answer for you, but I don't. Okay, so this is the interior of that chamber that I mentioned this is actually, you can't count all of them, of course, because you only see some of it. That's all of the openings for the 192 beams, and whereas this is very small, that's the thing where all of the laser light's going to go in either that side or the other side, okay? But
Is that a human on the left?
yes.
What?
That-
That's the scale?
I
Yes,
thought that was a giant pencil.
that's right. So this thing over there...
It's a nuclear pencil.
Yeah, that's
Yeah.
right. So
Yeah,
this
look.
thing over there is
Everything's
what is,
valid.
they are aligning this little guy over there to be in the center of this big chamber so that it's at just the right place because they don't want it to miss the lasers, obviously. And so this is very big. The thing that they have to, to line up is really small in comparison to the physical size of this.
How often does Professor X show up there to find all the mutants?
Are those chew marks on the pencil?
No, but that's a very. It certainly looks like.
What are those?
I don't know. I bet you. I'm guessing that it's something that allows it to rotate a little bit, just
Maybe
in
there's
case.
like a neurotic giant.
Maybe.
I think so.
Lauren,
Yeah.
what are the images on the bottom left and the bottom right then?
I'm going to answer in a minute, but you have a question.
All right.
Yeah. Oh. It's getting hot in here.
Just are you?
The sexy factor just dropped like 50%.
Well, I'm wet.
He needs you to dry him off. Sorry.
The chamber that you're heating up that emits all the X-rays, it looks like it's open on both sides.
Yes.
Which, if you're shining lasers into there, I would assume you'd lose a lot of energy out of the sides through reflection and just gaping holes. I mean,
This cat is hip. Yes.
So
Why'd you
how
take
do
off your wig, dude?
Huh?
Because I assume
Oh.
people behind me need to see.
Okay.
Yeah.
Kind of you.
But the person behind you doesn't need to see?
Okay. go on,
Well,
yeah.
okay, but no, that's a good question. I mean, the reason that those holes are there is literally just to let the laser light in. But as the thing heats up, what do you think happens? And we'll be talking about this a little bit later. As anything heats up, it generally expands. And so what actually happens is that the laser entrance holes, they're called LEHs, the laser entrance hole contracts because the rest of the gold is expanding, okay? And so, in fact, what happens is that as the thing gets hot, it starts to, like the field of view, it starts to see less of the lasers. And so the experiment ends up being over relatively quickly because of that. And so, but it's timed in such a way that if the fusion was going to happen, it had to happen before that anyway. So, fuck it. You know.
Fuck it. That's good. That's a great segue to the next question. Fuck it. Okay.
Yeah, so that is the little pellet, and to answer your question, one of you, the baked Alaskan thing, they're experimenting with using different things to hold the deuterium and tritium in there. What have they used thus far? They've used a particular kind of germanium doped plastic. It's a glow discharge polymer, so it's mostly carbon and hydrogen. And then they're also now using diamond, in effect. And then they're also considering using beryllium, for various reasons, and we can go into that later.
All right.
1 second.
So this is aligned in 4 dimensions, right? Because you also have to do time, because these are pulsed lasers.
Absolutely. Very good question. Very good point.
Wow.
So in order for this, that's right. And actually, I wasn't even going to get to this much, but it's actually one of the most subtle and difficult to design aspects of this whole machine is the time dependence of what the laser energy has to look like. In fact, if you just come in with one big pulse, then what that does is it shocks this pellet a lot from all directions, like I described, making it very hot and dense, but it doesn't get as dense as if you were to repeatedly shock it with 4 smaller pulses. In other words, more small pulses is better than one big pulse. I'm not going to go into why that is, but it has to do with just simultaneous conservation of energy and momentum. But the result of that is that they actually have a train of 4 laser pulses that have to be very precisely timed so that they coalesced in such a way to maximally compress this deuterium and tritium baked Alaskan thing.
Yeah, so fuck it. All right. Is that correct? Okay.
And before we
Whoa.
move on to the next slide, we do want to thank our viewers at home. We are live streaming this via YouTube, so thank you so
Hey.
much for checking in with us. And you guys can all tell your friends to check it out at home as well. Thank you for watching.
Yeah. So here is again the actual capsule in comparison to a giant eye and a giant finger. No, I'm just kidding. And then this is a cutout. This is a cutout right below it of what is in the capsule, and this is an important thing. So the meringue, so to speak, is in this case it's I guess it was a diamond as depicted there. But notice that there's 2 different regions inside that are colored blue. And they're both this 50-50 mixture of deuterium and tritium. So both of them are heavy forms of hydrogen, okay? But there's gas of deuterium and tritium that's not very dense. But then there's ice. Now, why do they do that? They do that because they want to cram more deuterium and tritium in there so that they have a better chance of getting fusion. But guess what? Deuterium and tritium ain't solid anywhere near ambient, room temperature and pressure, right? You have to go way cool in order to make hydrogen solid.
Cryogenics.
Right. So this whole capsule, counterintuitively, has to be kept at 18 or 19 Kelvin. Okay, so room temperature is like 300 Kelvin, 298 Kelvin. And 1 Kelvin, again, is 1 degree Celsius, which is bigger than a Fahrenheit, right? So, so this has to be, this has to be really, really cold, and yet, ironically, the whole point is to make the damn thing really hot after it gets whacked by the lasers. But they're doing that in order to make it so they can push more deuterium and tritium in there, so that there's more to do the fusion.
Because not every single, if you put two atoms, they're not just going to fuse. They're going to, whether they're at a hot or really, really hot or really, really, too much
And we'll
fusion,
talk a little bit about
fusion.
that. Yes, go ahead.
Was it better to have just a really cold room rather than actually just increase the pressure? I guess they probably
Well,
considered that.
that's an insightful question. There is a trade-off between temperature and pressure in general, and we'll be talking a little bit more about that as we go on. But yeah, in general, I think as you were correctly intuiting, as you heat something, it wants to expand, and so there's a weird.
Instead of having a temperature at 18 Kelvin, you could have a higher temperature with higher pressure.
Well, it would just be harder to stuff in that amount of deuterium and tritium in there, as it turns out. And so they wouldn't be able to get that in there. They can get other stuff in there, but that other stuff doesn't fuse in the way that the deuterium and tritium does. So that's kind of the thinking there, I think.
Yeah, that's what I was thinking too.
Also, Matt,
Yeah.
Matt, does
Not
this
gonna
all
work.
check out on the nuclear fusion degree? Does this all check out?
I think that was third year, so I don't.
You didn't get there. Playing hockey.
So now what the things are on the upper right there are simulations done by colleagues of mine with material models made by me for how this stuff behaves when it gets compressed and heated, for what happens as you go on in time. It's like a cross section of this little capsule as it's imploding. And what you see here, and this is important, what we want is for this thing to be basically spherical. We don't want a whole bunch of shit to just spill out, because if it spills out, then
That's the
it's not
technical term.
right. Then it's not getting crunched in the
Shit
same
eye
way.
is the technical term.
But
Too much shit eye.
even in the idealized simulations, when you have two fluids next to each other that have different density or different composition, think let's say you pour cream into coffee or something, you get this swirly thing, right? And so, I mean,
Now you're speaking my language.
okay.
The hip movement helps too. Did you see that? Okay.
So I mean, the thing is that this stuff has all kinds of ways of spilling out when it starts to get dense, and the more dense it gets, the greater the tendency for it to want to come out, just like the milk and the coffee thing. So they spend an enormous amount of time, the people doing the laser jocks and this stuff, trying to change the relative intensity and timing of these beams so that they sort of trick the thing into wanting to be spherical. And this is an actual image, an X-ray image, in fact, of X-ray emission from the actual fusing thing of what it looks like. And you can see it's about as round as they can get it these days, but they also know that it's not as round as it needs to be to really have the sort of gains in terms of making a power reactor that they want.
So in the cafeteria,
Yes.
I'm back.
do
they have mac
when
and
you
cheese?
guys go on break, is this the kind of shit you're talking about at lunch? Or do you talk about dating and shopping and what do you talk about
I
at
have
lunch break?
never heard anybody talk about either dating or shopping.
Cool.
Yeah.
What do you talk? No, seriously. I'm sincerely
no,
curious.
no.
A bunch of
Physicists be shopping.
I basically we talk about this stuff.
you never take a break.
Well, no. Well, here's
Just
here's
came
ano-
back from Hawaii. You took a break.
I'm going to enact a typical conversation
Please
do.
between two
Can
physicists.
I pretend to be the other physicist?
Yes, but
Okay,
you
great.
better do a good job.
Okay, all right, I got it.
So it's
You gonna
so it-
fire her? Jesus.
Wait,
So
wait.
it's-
Can I be like a new physicist trying to get a job?
Yes, you ready?
Okay, yeah.
Okay.
And this is the sexy physicist that
cafeteria?
just comes
Hot
in.
guy physicist.
Okay.
It's like a
We're in the
porno.
we're in the cafeteria though. We're all in the
Yeah,
cafeteria.
yeah.
It's pronounced cafetorium.
Yeah.
Wow.
Carry on.
So yeah, this stuff is really interesting. I can't wait for you to work on it, but the funding's getting cut again.
Funding.
Yeah. And oh boy, these Washington idiots. Oh, I know what I'm gonna do.
There's just no money in it anymore.
So that's also a typical conversation.
That's the end of our talk?
That's it.
Wow, you're cold.
Not colder than these nachos.
Oh. Or
Did I
what's
get
in
the
this
job?
little pea? Okay.
So wait, I'm sorry. I'm not finished. So I'm sorry. So this is what I'm really getting at. Does this machine that you have ever get tired?
Oh, yeah.
Now, when you go to lunch, do you want to give it a nap, a break, or do you like
No.
enjoy operating it until it? Do you run it like a rat in a thing until the rat just dies?
Yes.
Okay.
That's a beautiful metaphor, I think.
Okay.
But you'll also see
Okay.
a lot.
Like
lot,
a rat in a thing.
Yeah. A lot of the people that are at this place, they're like pretty serious bikers and hikers and
bet.
and likers and
Yeah.
whatever.
You got to
And
put
so-
some of that
yeah.
somewhere else sometimes.
Yeah.
Okay, thank you.
So
Wow.
I want
I'm just tired listening to you talk. I don't know what the hell you've said, but I'm tired.
Many scientists
We'll
have
go
that
shopping
genius
after this.
and just like want to focus on one thing. I want to quickly ask. So you said that you specifically make the model of the P that then goes inside of the gold cylinder.
Yeah. So what my main job is to construct what are called equations of state, which, as I'll show in a subsequent slide, is the relationship between the pressure that you apply to something, the amount of space that it occupies, and the temperature that it's at. Basically, making the point that I think she was alluding to, that there is a trade-off between these things. You heat something up, it wants to expand. So there's a relationship between pressure, temperature, and density or volume, and that's sort of my job, is to use the best available scientific tools to figure out what is the equation of state for hydrogen, what's the equation of state for the meringue part, and all this, so that they can model correctly what happens when the laser hits this stuff.
Could we just call you a P modeler?
Yes.
Is that easier? It's the cafeteria talk,
That
right?
gets, it's a little close
get
to
that.
home because I was a bedwetter till age 14.
Okay. We'll talk about that in a little bit. Let's move on, though, to the next question.
So
If you want to work at Lawrence Livermore, this is what you have to do.
I pooped.
What
the bed.
is an example of, so we're going to, but it's mostly going to be questions from now on. Go.
Wait.
Yeah. Anybody else want to answer this? Let's read it out. What is an example of fusion power from which we are already benefiting daily? That's a hint.
The sun
Okay.
and the
The
stars.
sun. Did she get it?
I just said it.
Yeah.
She did.
Go to the next
Eu-
Yeah, I said it.
Eureka! I think that's the sun. What are we giving her? There's all these little dudes down here. Ooh, yeah, okay. You want to pass it out? This here, show it to the audience. It's a cat laser. We got this from Lawrence Livermore's souvenir shop.
Which is located between the two cafeterias.
Yeah.
There's
between the two
191 more
cafeterias.
of those.
Lots of parking.
So you too can try to create nuclear fusion by, I don't know, shining it at your cat. I have no idea how that works. But you got it. Sun.
Now, the kind of fusion that happens in the sun, as I was telling you in the beginning, I'm not an expert in astrophysics, but I was cramming for this show actually yesterday, and so I learned a little bit about it, and it's actually quite different from the kind of fusion that we're trying to do at NIF. The kind of fusion that happens here happens in stages, and I won't go through all of them, but it's actually just bare proton guys coming together, so hydrogen rather than deuterium and tritium, at least initially. And so it's actually much more complex than what we're trying to do, but it happens all by itself because it's so big and massive, and so it gets hot, and there's the gravitational energy that contributes to that.
And then it's at perfect equilibrium so that the gravity and the pressure are constantly smashing together.
Yep.
Nuclear fusion is
Yep,
occurring,
yep,
and that's
yep.
how everything's being lit in our
I
solar
think,
system.
I think that's correct, yeah.
All right. Yeah, in cafeteria lady? Anything?
I was just napping.
Oh, you were
I don't know.
napping.
Yeah.
Okay.
And then hopefully some of those photons that leave the sun and hit your solar panels at home can power your houses and your cars.
If you have one. All right, yes. Feel empowered, no pun intended. All right, next question. Should we jump on in? Here we go.
Okay, so what might be the benefits of nuclear fusion as a power source as compared to, for instance, nuclear fission?
Thoughts? Here we go.
It doesn't make us dangerous of remaining components from the
That's
fusion.
right.
That's correct. Eureka! Nailed it. Next slide. Here we are. All right, this is definitely it, my friend. You can put this maybe above your bed. Huh? The ladies like that. Radioactive materials. This guy. Here you go, sir. Woo! Good for you.
Yeah, so I mean, when nuclear fission is the thing where you get really heavy elements that they break apart and they release, they end up have daughter products that are less heavy elements plus a bunch of energy, And that usually the daughter products are things that themselves are radioactive enough that you could, that they're yucky to deal with. And you could also, when I say proliferants here, you could make bombs out of them. And so it's a little bit of more of a security concern and things like that too. So let's go back to the kind of fusion that's at the National Ignition Facility. If deuterium and tritium, it does make this energetic neutron that, of course, if it's allowed to go through a bunch of stuff, that could mess some shit up too. But it mainly produces helium, right? And helium just makes you talk like this. It doesn't. Is nothing particularly bad about it.
We wouldn't turn into zombies. We'd just be like, oh, okay. That's safer, I guess.
Nope.
No, she's still napping. We'll wake her up.
Next question.
Okay. Oh, we still had.
Oh yeah. This is just talking about equation of state if I hadn't mentioned it yet, so you need to squeeze and heat this deuterium and tritium thing a lot for it to fuse. So we need to know how hard we have to work to compress things, and all that kind of stuff. So that's this relationship between the pressure you apply to something, the volume it occupies, and the temperature that it's at. So since that's my expertise, that's what a lot of the subsequent questions are going to be about. I'm going to break the fourth wall here.
Yeah.
How are we doing on time?
We're doing fine.
So-
Those are quick.
Yeah, so I don't want to. Should we slow down a little bit?
We're totally fine. I would relax. You're not at work. You can just enjoy yourself. We will.
It's like we're at the cafeteria.
How are we
Red
on
cafeteria.
temperature and pressure?
Audience,
yeah.
How are you guys feeling? Are you guys feeling good? Yeah?
Yes.
Feel like you're learning something new?
All
Yeah?
right.
Good. You guys have any questions right now?
They're slowly absorbing it.
Should we take a question? Let's from
Let's
people
take
that
a
have
few
it.
questions.
Take a few questions.
All right.
Yeah, I have a question on, you said that the P thing isn't as round as it should be to actually facilitate a nuclear fusion reaction, to use it as a power source for a replacement of the way that we get power currently. So if this is successful, how would we go about doing that, getting that as round as it should be?
Well, okay, so there's a number of answers to your question. One of them has to do with how round it actually is before the laser even hits it. So in other words, that's kind of an issue of how round can you make a little sphere, because as I think you're correctly figuring on, if there were any imperfections in it, let's say a little dust thing, this is why everybody has to be in clean suits in the place. If there's any dust on the surface of this, that will create an asymmetry that then gets magnified when the thing is compressed. So that's right. So I think my understanding of it, which may not be complete, is that I think that they're making the thing round enough. That's not the sort of the limiting factor. The limiting factor really has to do with, in a sense, the way in which this X-ray radiation from the gold canister makes its way into the thing, and how uniform or non-uniform that is in its sort of angular distribution, right? And so I think that that's a slightly bigger concern than the sort of native roundness or lack thereof of the P.
Okay,
All right.
Are there any rooms in the buildings that are like the room in Men in Black where they go in and they have to go down a lot of levels underground, and there's cool aliens and other stuff under the ground of the building? Are there any cool rooms that do
That's
secret?
the dirty room.
What?
The dirty room.
The dirty room. Are there any dirty rooms? No, but I really want to know, are there
I
like
love
cool
where your
rooms?
mind goes.
He did that. Okay. Are there any cool rooms that are like and then and you go down?
Yeah, actually, in NIF itself, in that building, there's a lot of zzz and
Is there? Really? Like for rooms or for laser stuff?
No, rooms, yeah, rooms.
What do you mean?
Well, I don't even know what this shit is for. I just took a tour of it, and I heard a lot of
You're fucking lost, too. You're just
But there is a lot of secret stuff in my lab, too, because it's also a national security laboratory. So
okay, aliens. Have you seen any at work?
Only foreign nationals.
okay.
Got it.
We're not being xenophobic, by the way.
All right, well, let's take another question right now.
Hi. On the slide with the photograph of the microwave emission of the small sphere being...
X-ray emission, I think. But yeah,
yeah. On that photograph, it said something like 661 kilojoules. Is there a simple analogy that tells us how much energy is being released by that laser at that level?
I can't think of... Let's put it this way. 1 joule would be like maybe, let's see if I get this right. I mean, it's kind of, I think it's sort of the, like if I just push on this guy a little bit just with my finger, that might be like, I don't know, some fraction of a joule or something. I mean, that's like a typical mechanical thing, because a joule is basically, it's a Newton, that's a unit of force, times a meter. So it's basically the amount of force that it takes to accelerate something through, a distance of 1 meter. And a Newton is a kilogram meter per second squared. So a kilogram is a macroscopically sized thing. We each weigh some number of them, right? And so that's like the macroscopic stuff that we know for our everyday experience. So kilo is 1,000. So if it's 100,000 joules, and yet this thing is so damn small, that's a lot of joules in some small little thing. So I mean, that's about all I can say.
A lot of joules, dude. And then I wouldn't even dare ask what these numbers here are.
Well, yeah.
Delta lambda, what is that?
Yeah, so this has to do, and this is something I only have a dim understanding of myself, but these laser jock people, they've figured out that if you slightly shift the wavelengths of the actual light from these different adjacent beams of the 192 beams, they mix in slightly different ways to then conspire to make this thing a little more spherical as it implodes. And so they actually, in a sense, detune the lasers a little bit on purpose. And I can't go into why that is. It's a bit technical, but so that has to do with the wavelength difference between the different adjacent beams.
So, once again, I'm just going to need a little more specificity just to track you. When you say, I can't make a joke about it because I can't repeat a single thing you said.
I like the that was good. Yeah.
I could make more sound effects.
I think we may need some.
Okay.
All right, should we keep going? All right. Absolutely. Here we go. Next question, guys. And we got...
Most solids and liquids expand when you heat them. And why is that? This is a little bit of a weird question, but go ahead.
Right here.
Molecules are excited, therefore they are moving around faster.
Okay. I'm not sure if I'm going to... That's part of the answer. So I'll give you partial credit. You have partial prizes,
we have
right?
Partial, yeah.
That's not wrong, but there's another piece of it.
Well, when they move faster, they heat each other, and when they heat each other, energy is released. And because energy is released, it's like an exothermic reaction that releases.
No,
Ooh,
that I'm not.
Maybe
try the guy up there. There's a guy up
let's,
there.
let's see if the comics have an answer. You guys have any thoughts?
What was the question?
Yeah, go ahead. Let him take a guess.
Yeah. Take a guess.
Us?
Yeah, go ahead. Go for it.
Most solids and
Associate
liquids
degree.
expand when you heat them because they're upset about stuff.
No, that makes sense. Yeah.
No?
Emotional?
Okay.
No.
Most solids and liquids expand when you heat them because, damn it, when you're cold, you put a sweater. I don't know anything about any of this.
Yeah.
I'm upset.
In there.
Noises? You want to hear noises? Okay. That's why? Is that what you said?
Noises.
I have a question real quick. I'm sorry. Let's get back to this. I want to hear, how many people come to this show because science is you're really interested and curious about science? I'm just really curious about this. Cool.
All right.
That's so
Yes.
interesting. Yeah, look at that. They're all of them.
And it's our job to ruin that.
Awesome. Cool, thank you. Just curious.
All right, let's...
Hot people?
Oh, there it
This
is.
guy.
He's crushing it here. We should have you as the image of the sun. Okay.
All right.
Is anyone hot enough that they're expanding right now? Is that?
Why do you think I'm crossing my legs,
guy's
buddy?
expanding back here. I think there's an expansion in his seat.
All right.
Release energy.
Because molecular bonds are being
He's answering up here, I think.
because molecular bonds are being weakened.
Yeah. Say it one more time.
One
I think
more
what you...
Because molecular bonds are being weakened.
Yes.
Molecular
That is
bonds are being
weakened. Go to the next slide. So
Wait. That was a Eureka moment?
Eureka moment.
Yes.
Woo! Give us some for you too, my man.
So
let's give some nuclei to this guy here as well.
So of course, solids. This is an artist rendition of a phase of ice. So that's just solid water. And of course, you have atoms and then little molecular bonds between them or whatever. And then the thing is, this is the this is an artist's rendition of the energy, the potential energy between two adjacent atoms as a function of the distance between them. So over here, they're at the bottom of the hill. That's where they like to be, right? So that's the equilibrium distance. So that's the distance that you would find. As you heat the thing up, these things jiggle around. So you're partially right, but what happens is that when they start to do that, they're going to bounce and bounce and bounce. And when it's heated up enough, they're going to be bouncing like this. And then what he said comes into play, which is that this. Basically, the force, the farther out you are, the weaker the bond is, and that's really the reason that things start to drift this way. So you can see that if I'm bouncing between here, my average position is this. If I'm bouncing between here, well, my average position is maybe here. I'm at a bigger separation than I was before. So it actually has a lot to do with what both of them said. I'd like you guys to give full credit to him and half credit to him.
Yes, teacher. You guys, great job for both.
So quickly,
credit is still an F.
Credit for that one.
So Lauren, this is explaining that if it's too hot, they'll bounce and they won't break the molecular bond, and if it's too cool, it will also not break it.
Well, this isn't really an issue of breaking. I mean, I'm not talking really about here I'm talking about just expanding. I'm not talking about like when the stuff completely flies apart. So this is just like the normal thing of, you have, if you have a bottle or something where the bottle cap is metal and it's been cold for a while, maybe it's hard to get it off, and you put it under warm water, and then it's easier to get it off because the metal expands more than the glass thing that it's surrounding. That's just that if I made this curve for the metal thing, it's like this. If I made the one for the glass thing, maybe it's a little more peaked, so the metal's expanding more than the glass part. That's all. So we're just talking about when the stuff is still in its kind of packed in state, not when bonds are breaking per se, which is why I gave her the
Oh, yeah. Well, we'll give you something at the end. We'll give you
a hug.
A hug. Okay, that's very sweet.
From him.
Yes.
From Sunman.
You don't know what you signed up for, Matt. The next question, you're going to take your shirt off, by the way. All right, we ready to go?
Oh! Get naked.
His shirt's expanding. It's just this part here. It's just, he's at this level. Okay, we're going on. You ready? Here we go. Boom.
Let's have
the so since we're talking here about things that start basically like this P is solid on the outside, then it's got a solid layer of this deuterium and tritium ice, but then it's got this gas in the middle, and then when you whack it with the lasers, then the whole thing kind of liquefies and all this very quickly. And then I'm talking about, we're worried that some of the stuff in the middle is going to spill out because it's like when you mix two fluids together. So it starts solid but becomes fluid, and that's why the stuff is being able to, leak out. So what is the substantive difference between a solid and the liquid, really?
Okay. Let's see, associate degree, cafeterium, any ideas? Any thoughts? I don't know.
Let's take the comedians first. Let's
see.
Well, if I knocked over a glass of solid, it wouldn't have gotten all over my lap.
That's right. That's good point.
That's right. Partial credit.
There it is. Substantive. I like how you added that.
Yeah.
So I know. All right. Any other thoughts?
I just sincerely would be wondering if it's just the substantive difference between a solid and a liquid. Is the speed at which the little guys inside are going like that?
I would give partial credit to that. Actually,
Thank you.
On the straight up, yeah.
Thank you.
But there is a more precise answer. Let's see if
more precise than. I don't know about that.
Who hasn't answered a question yet?
Who's not raising his hand? I want to understand that dynamic.
Okay.
Just the energy state of the different. No.
I love the sound effects of this show. We're really just pumping it up.
Okay, we have another volunteer for.
The molecules are tightly packed and solid.
Not necessarily. It's a good supposition, but it's false. You can have a liquid which is denser than a solid, so that's not really the distinction. But good try.
All right. Somebody else who hasn't been called on before? Okay.
I'll give it a shot. Is it that a liquid takes the shape of the container around it and its own structure?
I would give partial credit to that. Are you guys?
We're
partial
telling you,
credit?
yeah, partial credit,
Yeah.
absolutely.
Yeah, you gotta make sure that. Yeah.
Oh, here it comes.
That's
that's a catch.
That's getting there. That's getting there. Next.
Cool. All right, we'll come down here.
Okay. Brainiac trust here.
In a liquid, the molecules are able to slide over each other, and the bonds aren't very tight.
so-
whereas in a solid, they're
full
more
credit.
tight.
Wait, I want to hear her say the thing. I don't know the thing. I have no brain at all. Like
Just
you.
look up here. This makes
Yeah, he was
perfect
gonna-
sense.
No,
He was going to give a better explanation.
Eureka!
Go ahead.
Oh, look at that. That's a squishy big one.
So the way that we would technically say this is that solids do not resist shear deformation. So what is shear? It's I'm going to use a
Pantyhose
politically
thing.
incorrect
Pantyhose.
term. It's the Native American sunburn. You know, the Indian sunburn thing, like this. Right. So
You want to demonstrate that on a? I'm
Yeah.
Lucky.
Yeah. So
Oh, great.
Not on me.
Now that okay, good. Yeah.
thing like this, where I'm not actually doing it, but
It hurts.
I think you should actually do it.
Yeah, you probably.
So yeah, when let's say the upper part of it's moving this way and the lower part of it's staying still or moving that way, so it's exactly this business of sliding things over each other. That's called shear. So solids, technically speaking, resist shear. So that means that if you try to apply shear, then it springs back. A liquid does not. Now, why that's important for this whole fusion game done with lasers is exactly this business. Let's say that this stuff out here were solid rather than liquid at the point at which it's sort of in its final crunch. Then there wouldn't be enough of these fingery things in here because a lot of the stuff would be more kind of retaining its original constitution. But if it's liquid, then it doesn't resist shear, so that's why there's more finger-like instability. So in addition to understanding the equation of state, which just has to do with what's called compressive strain, like, compressing something like this, we also have to understand this business of the propensity or lack thereof to resist shear deformation, or the Indian sunburn kind of thing.
All right. It looks like a hand, too, by the way. I just thought I'd throw my scientific knowledge in there.
And then does something similar to that happen when it goes from a solid to a liquid, and then from a liquid to a gas?
Well, that's an interesting question. The distinction between liquid and gas is far more subtle. So, actually, technically speaking, there sometimes is no distinction. It depends on where you are in pressure and temperature, and what the material is. There can be literally no distinction between liquid and gas. A gas is just like a less dense version of a liquid. If you go to low temperatures, then there can be a difference. Basically, it's this whole business of condensation, like when you go out in the morning, maybe not here, but where it actually gets cold, Well, I guess San Francisco gets cold. I live in the East Bay. So, when you get condensation in a window in a car, for instance, that's when you have little droplets of liquid that are forming out of the gas. So that's a situation where you start with, let's say, the atmosphere, and then if it's cold enough and if it's moist enough, then you'll have a phase separation, where you'll have liquid, which is more dense, and gas, which is less dense. So then there is this distinction, but if you were to heat it up, you wouldn't have condensation, which means that you're going seamlessly between gas and liquid.
Makes sense to
I
me.
think I just became a gas.
What's that?
I just expanded into the gaseous
Oh, you did?
state.
Oh, you
Yeah.
did? Okay.
Yeah,
Thanks
not
for
like
giving
in
me
a
heads up.
farty way, but just like my mind is so blown, I don't think I'm like constituted like a person anymore. I've just dissolved into space.
It's transcendent.
Thank you.
Yeah, it is.
Yeah.
Thanks.
Let's transcend to the next question. You guys ready for this? Here we go.
All right. So, this is maybe an easy one, maybe not. Why is it so difficult to do this fusion thing in the first place?
Comics?
Well, let's start with the people who have the least idea. What do you?
Is comics the reason why it's difficult?
Hard to fuse.
Hot guy?
Maybe
Go.
come back to like your parents' divorce or something. I don't know.
Did anybody ask the nuclei if they wanted to be together?
That's a very,
That's
very
a good question.
Like, no one has raised, we've been talking for an hour, and no one has brought up consent once.
That's a good point. Consensual nuclear fusion. You're a progressive man.
I just think we're asking the wrong questions here. Listen.
That's very good.
Fair point.
Why is it hard to fuse any two things together, really? At the end of it, why do I keep talking to that guy?
I don't know. I'm just hovering creepily
Because
behind you.
communication is the key, and most people are uncomfortable with the vulnerability that is required in communication, and nuclei are the same as us.
Nuclei are our people, too.
Yeah, it's true.
Exactly.
Should we just move on to the next question? Did we just nail it here? No, we didn't.
All right, audience, do we have any guesses? Let's.
Nailed it in one.
Oh, he did? What was it?
Okay, why don't you explain it? Explain it.
Nuclei are charged, and that they have this electrostatic force of charged particles. Inverse square.
Eureka.
Eureka, everybody!
Yeah!
All right. This one, we can take it out. It's a.
It's a protective coverall with a hood.
Why don't you open it up for a sec? Open
All right,
it up,
give us 1 second.
and you can see what we got you here. I think maybe if you visit Lorin at Lawrence Livermore, you can wear this.
I'm trying to get them, by the way, to change the name to Lawrence Livermore, since my name is Lorin. Lorin apostrophe S Livermore.
You can't just throw
They
a
haven't
can of spray paint, a little apostrophe in there. You can.
I'm not strong enough.
You're not strong enough. The bonds are too great. Let's
Have you tried heating it up?
Oh, that was so easy.
Oh, wow. He can open up a jar of pickles. Let's open this up.
What is it?
What do we have here? Oh, it's your own biohazard suit.
Yeah, that's what I'm talking
Yes.
about. Yep.
You too can conduct experiments in your garage.
Well, we are in the Tenderloin.
That's right. If you could put that on.
That's what
There
they,
you go, sir. Yes.
Yeah, that's what they wear on the Men in Black level. After the.
Now, I have a quick question. Will he be wearing that when he cleans the house?
No, just to bed.
Oh. Who's that to protect, you or him? I don't know. All right. You're looking good.
Oh,
Look at
dang.
that.
Yeah.
He's got it. Give a
Wow.
round of applause.
Woo!
Put it on, everybody. Look at that. These are the Lawrence
He looks a little like, I don't know, many of you are too young for this. He looks a little like one of the Coneheads from Saturday Night Live.
There it is.
music.
Excellent. You got it. He's ready. All right.
Yeah, so he is exactly correct, Mr. Conehead guy, which is the so since the deuterium and the tritium are both charged, positively charged, right? We know that like charges repel. So in fact, the closer they get to each other, boy, they really don't like being close to each other, and they only start to like being close to each other. You can think of some jokes. They only start to like being close to each other when they're already really close. So when they get to be, I don't know, a few times 10 to the 14 or minus 14 or 10 to the minus 15 meters, that's when the attractive so-called strong force kicks in, which makes them want to bind together. Prior to that, they want to repel each other. So that means you have to slam these sons of bitches together in order to get them to go over this barrier so that they want to be there.
So then is the weak nuclear force the one that keeps all atoms apart right now?
No, this is the strong nuclear
I know,
force.
and then the strong is when they bridge the weak.
The weak nuclear force mediates basically, in a sense, transmutation of protons to neutrons and back and things like this. So that's a more subtle thing that I haven't discussed here, but is actually relevant for I believe for the fusion in the sun more than this.
So two protons will repel one another, and then repel, and then if you get them hot enough or pressure enough, then they'll.
Yeah, and yes, that's right. And the reason that we use deuterium and tritium rather than just the protons that would be in the sun, for instance, is because that reaction happens a little more easily and gives off a little more energy. So it's easier for us to click the done box and trying to make fusion.
That's how it works. You click the done box and boom. That's it. Okay. And so what's this Coulomb barrier? Am I pronouncing that correct?
Yeah. Coulomb is some scientist who was, I think, the first person to think about it. So it works the same way as gravity. Electrostatics, so this is just the electrical part of the electromagnetism thing of force. You have two charges that the force between them varies as the square of the distance between them, and it's proportional to the product of the two charges, okay? So it's like charge 1 times charge 2 divided by the square of the force between them, or the square of the distance between them, excuse me. That's what the force is. And then...
I work at McDonald's.
And so Coulomb was the guy who first, I think, realized that having to do with charges, but it's exactly the same force law for gravity, but where now gravity, of course, is purely an attractive force, and there you have the mass of one times the mass of the other divided by the square of the distance between them, and this is the charge of one times the charge of the other divided by the distance between them so the closer they are, the more they repel with each other if they have the same sign of charge, both positive or both negative.
This could also be like a graph of my time on OkCupid. If you look like they meet me, attraction, then over time it's just repulsion, repulsion, repulsion.
Or any marriage ever.
Any relationship, really.
No?
Nothing? Nothing, people?
Well, we know who's polyamorous.
What's that?
Well, we know who's polyamorous.
No, what?
I don't know who's polyamorous. Any you have any questions on this, or is this just like crystal clear to you? Silence.
These are pretty colors.
Yeah,
Yes, we have
I
a
died
question.
inside a long time ago, so I got nothing.
Is there any consensus as to why that changeover happens, why you go from repulsion to attraction all of a sudden?
I mean, I think there's a lot of consensus. I mean, it's basically just that the strong nuclear force is extremely, well, it's very strong and it's very short-ranged, and in this context, it's attractive. So I think people feel at least that they understand the strong nuclear force well enough so that it's not like a mystery. One thing that I will say, though, is you've probably heard of the quarks, things like this. So there's 3 quarks that make up a proton and 3 quarks that make up a neutron.
What's a quark?
Quark is the constituent of a nucleon. Nucleon being either a proton or a neutron. Again, there's 3 of them in protons and 3 of them in neutrons, and so the actual strong force, the sort of is the direct interaction between the quarks. This strong force I'm talking about here is really the residual interaction, which is much weaker than the pure strong interaction between quarks, which arises when you have, it's sort of, these 3 quarks over here that make up the proton and those 3 quarks that make up that proton, and then it's sort of, as they come close to each other, it's the dance that they do and what happens, I'm not explaining this very well. I want to use the term dipole-dipole interaction, but you guys don't know what that means. You probably do, somehow. Do you have a physics background? Oh, look at this guy. A ringer.
We're going to need that code back.
Okay, let's get to the next question, and then we'll get more questions.
Yeah.
Well, okay, yeah.
Okay.
I was just going to say, maybe this makes sense to us because we can imagine that there has to be some kind of attractive force in a nucleus that holds protons together. Otherwise, you wouldn't have anything heavier than hydrogen.
Can we give her a prize, even though that wasn't an answer to the, because that's exactly correct. That's exactly correct, and it's extremely insightful.
Here, catch the nucleus.
No, you got to give her something bigger than that.
Oh.
Okay.
There
well,
was nothing wrong with the size of that.
Okay. All right.
It's perfectly
Size of
acceptable.
nuclei.
That was a very, very good point that you made. Did everybody hear what she said? Did everybody understand it?
Nope.
Okay. Say it again. Okay, I'll explain it. The fact is that any element bigger than hydrogen has a conglomerate of protons and neutrons in it. Well, if protons repel each other electrostatically, and neutrons have no charge, right? They're just hanging around. Why would you want to get a bunch of protons together? Why wouldn't they always fly apart from each other? Because they're all positively charged, and they repel each other. So what she said is, well, there has to be a very attractive thing at short distances. Otherwise, you would never have a nucleus with more than one proton in it. Exactly correct.
We would never have carbon.
All right. Yeah.
Yep. Hold on.
Doesn't that feed into the fusion that's going on in the sun to produce higher
Yes, it is.
Yeah.
Because in the sun, again, I'm no expert on it, but from the little bit of cribbing that I did, I mean, there actually are a number of heavier elements that are in the sun. There's, up to I think iron. So that's
the point at which the star will thus then no longer fuse the molecules, and it will actually start to die.
Yep.
Cool. All right.
Iron supplements. Okay, next question. Here we go.
So this is a more subtle question. I bet he knows the answer. Maybe we should disqualify the guy in the white suit.
The lab worker.
Why don't negative particles, so when you have regular matter, just even us, this floor, that camera, whatever, why don't negative particles like electrons and positive particles just spiral into each other and annihilate if because we just said, like charged things repel, but if opposite charged things attract, why wouldn't they just want to get closer and closer and closer and closer, and then that's it? Why wouldn't matter implode on itself? That's my question.
Comedians, any thoughts here? You want to add your magical wisdom?
I think there was a different show I was invited to. And I wound up in the wrong dimension.
Dimension. You're totally.
Or room.
You're floating around.
I can't contribute in any way. I'm just going to be mildly attractive and sit here. How's that?
Good for you.
Thank you. I went to grad school.
Did you really?
Yeah.
What'd you study?
I'm not going to say.
Okay.
Humanities?
Performance.
Humanities? Is that-
Yeah.
Were you a theater major?
Yep. I have a master's degree in theater.
From the Mondat?
That's a real thing people do?
That's a thing people do.
That's funny.
Yeah, you just have to be mildly attractive. That's it. That's all that's required.
Only mildly attractive.
I do want to say one thing. I think that as I'm watching this whole thing, I'm like, it's pretty much already a solo show. Like if Lorin this is a solo, you could do his job and my job
I'm
and
not
their
trying
job.
to do that.
No, but you're doing
he's got hidden talents
You're doing
too.
an amazing job, and it's the up and down and the lights and the Let's
Yeah.
clap for
Round
him.
of applause
Yeah.
for Lorin. Yes.
Yeah.
That wasn't by design.
Just
No,
own it,
it's
Lorin.
just
It's that
happening.
you guys are lame.
Yeah, it's true. It's true.
Look at this
It's true.
guy. He is crushing. You just.
Who's negatively charged now?
Hey!
A lot of repulsion in the room, isn't there? Oh boy! All right, so let's move to a possible answer for this question. Now that everyone's self-esteem is dropped. Okay. What do we got? Any new person?
Maybe this is what I remember from quantum physics, but don't they spin in different shapes like S, D, P, F, and different levels?
I'd like to give her partial credit. Yes,
Partial
you're absolutely
credit.
right, but there's a sort of deeper reason that that's the case. But you're absolutely correct. That is a manifestation of the underlying thing that I'm looking for. Good.
Because of the protons, the protons and electrons repel each other, so they're all spinning in different directions. I can't remember that.
No, that's not, no.
I'll stop.
No, but
You're doing a good job.
But you said the word quantum, and that's certainly a part of it.
You should say the word quantum more often.
Quantum.
Yeah.
Okay, partial credit.
So molecules are
little breath
basically
here?
neutral. I mean, in general, they've already combined, and that's why they are there. But there are instances where we have like, what is it? That thing, the cloud down in the southern hemisphere where there are. I'm going somewhere with this, but so what is that? Ozone layer. Thank you. The ozone area where those keep constantly migrating with each other. There are instances where that happens, where they constantly interact. But
I don't know what you're saying.
generally, molecules are neutral.
Slip in the word quantum.
That's true, but I don't hear an explanation there for this.
This probably is not right at all, but is it similar to how satellites are just falling and then their trajectory is kind of tilted due to our gravity, but it just never makes it, and it just keeps falling, so it just is falling around it?
Yeah, so let me say something. Again, she wins huge points from me, because even though that's not actually the answer here, it's another point which is equally insightful, which is this sort of centripetal force kind of thing, or centrifugal, I forget which is which. So it's the fact that it's, there's
very disappointing.
I know. So if this is the center of something and then there's something going around like this, the fact that its velocity is perpendicular to the direction of the force is that. So let me say, your answer would be the correct answer if you only had two particles in the whole universe, let's say one electron and one proton. Then it is true that in a classical physics Newtonian world, what you said would be the explanation for why, if the electron was going like this around the proton, it would keep doing that. So that's right, but if you have a whole mess of these guys interacting with each other, I can guarantee you that wouldn't save you. So good, but not correct.
Close. We got one more over here.
Does it just have to do with the universal forces at work that basically the weak and the strong forces of the electron versus the proton and the nucleus, that basically they want to kind of get closer, but because that they're spinning in some of the other forces, it's keeping them at a distance.
So like balancing of forces that are acting in different ways.
Can we just say that it's
Yeah,
in,
go ahead.
How about that's just in the Bible? Is that good enough?
Okay, one more.
You know,
I'm not sure if this is the deep enough answer you're looking for, but it's because, I mean, the way she said, it's quantum mechanics, all right? So there are only certain allowed energy states for electrons, and in order for them to occupy that state, they have to be at certain, well, I don't want to say radius, because that's not exactly the way it looks, but they have to be at certain, like, positions relative to...
Orbitals.
Orbitals.
So I would say that is not really distinct from the answer that she
that's
gave,
fair.
but that's a sort of continued expounding on that.
Give the answer.
So how about it? You want me to?
Yes, let's find the answer.
Next slide.
I'd like to hear 60
Oh, that's obvious.
Hello.
It's the Heisenberg.
Why didn't
It's so obvious I didn't say it out loud. Why would I say that? It's
Triangle
so clear.
times triangle is greater than h over 2.
That's like 80%
We were talking about
Greek
that
to
before
me.
the show.
Does anybody know? But I bet you that there are people who know what this means. What is it? Yes.
Breaking Bad, I love it.
Yeah. So
Fancy pants.
what it is that if
What
you,
is that?
It turns out that for microscopically sized things, if you you can think of jokes for that too.
Yeah. You know, if you keep calling attention to the jokes we're not making.
Okay. I'm sorry. That's a good point.
They're quantum jokes. They're being made in
Also,
other
if they're
universes.
super obvious, and then you point them out, we double can't make them.
Okay, good point. Sorry. Okay, so if you confine a particle to some very small, let's say interval of space, then necessarily it has to have a very high kinetic energy or a high velocity. It has to be moving in a sense very fast. And the way we say it in quantum mechanics is that it has to have a very small wavelength, because there's this quantum mechanics mandates this duality between particle-like nature and wave-like nature. So something that's moving very fast has a really, really small, small wavelength, kind of like a high pitch for a tone, something like that. So what happens is that if the electron, through its attraction to the proton via the Coulomb interaction, right, the electrostatics, if it gets closer and closer, as it would want to do, to the proton, then it starts going faster and faster and faster, and eventually it just can't get that close that's where the whole molecular orbital thing comes from. And so you're right and you're right, but the deeper principle is that there is a sort of reciprocal relation between the how much you can confine something and what its energy is. And so it sort of can't be contained at a certain point. So if the electron has a certain general energy, there's no way you can contain it more than a certain amount. And that's sort of what the Heisenberg uncertainty principle is representing. So it's really because of quantum mechanics that matter doesn't implode in itself. In fact, there's a very famous professor of physics and mathematics at Princeton University, Elliot Lieb, who, in a sense, he wrote a really insightful series of papers on the stability of matter, literally proving that if you didn't have quantum mechanics, there would be nothing here. Matter would not be stable. It's a very insightful series of observations.
I'm wondering if maybe you two want to spiral towards one another.
I think that she's already spiraled.
Yeah, she's fused.
Hey, man.
She's a matchmaker.
Matter is unpredictable.
All right, should we jump to the next one? Here it is.
How is temperature? So we're talking about things getting really hot, and they have to get really hot in order for this fusion thing to happen. Because again, the deuterium and tritium guys have to come screaming into each other very quickly in order for them to overcome the repulsive barrier and feel the attractive barrier of the strong force to fuse. Then they have to be very hot. So, but if we forget about fusion for a minute, how is temperature conventionally measured?
In detail.
Yeah. Well, not the unit, but what's the physical process that allows us, or physical processes that allow us to infer what the temperature of something is?
I think somebody back there had an idea.
How much thermal energy it radiates?
Okay. That's correct, and I think we should give him full credit, even though
Yeah?
that wasn't the answer I was looking for. But that's
Eureka! We're getting ooh.
That is absolutely
Squish ball.
You don't have to take it. That's fine. Just throw it right back.
that is absolutely
catch and
one of the
release
ways in
prizes.
which you can measure the temperature of something by the spectrum of electromagnetic radiation or light that emits. And of course, in the normal sort of terrestrial environs in which we live, that would be in the infrared. So you could use infrared cameras and things like that. So you're exactly correct. What I was thinking of something even simpler, which is like a standard mercury thermometer. What happens is that if you put into contact with something like one's nether regions, then the
leave it to these guys.
Okay. Then
Solo show. Boom.
So then the because of what we talked about before, which is thermal expansion of a metal, the hotter something is, the more it expands, then this mercury will, that maybe at colder temperatures would fill a small space, ends up expanding and filling a bigger space, and then you read off higher temperatures.
Yep, hold on.
Well, I guess my question is then could you use density also?
And density and the volume that something occupies, those are exactly related to each other. So that's the same, saying the same thing. Exactly right.
Does anyone in the audience want to come be like a backup dancer? I think it'd be cool if there were people dancing in the background, and maybe we could get anybody a musician? We could have a little music, little guitar guy in the
A little
front.
cabaret action?
Yeah, no, it's like a whole thing happening.
Actually, we have two very high-level dancers that are sitting in the back room,
Oh,
both of whom I
really?
know,
Ah.
and both of whom are sisters, by the way.
Really?
They have a
Nice.
very excellent
Yeah.
company called Sharp and Fine that you should check out.
Oh, interesting. It's gonna
Spiraling
get weird.
into
Fantastic
this.
choreographers, by the way, just saying.
Oh, and these are definitely the most complicated slides we've had on the show. It's like without a doubt,
Yep.
these are like mind-expanding slides.
Let's forget about this
Okay,
one.
forget
but-
about this one?
Yeah, we have now two answers, which was you correctly pointed out this thing about spectral emission of things, and the other one is this thermal expansion we talked about before.
All right.
Yeah.
We got another. Ready?
But give it up for Lauren for giving a Explain Like I'm 5 version of nuclear fusion.
Yeah, let's give it up for that.
And before we move on to the next slide, let's check in at home. So thank you again for checking in on the live stream. We are here having a blast in San Francisco at PianoFight. The website is eurekacomedy.com, where you can find all of these videos afterward.
All right, here we go.
How do you think we can measure temperature or infer temperatures in such extreme conditions like when we're approaching fusion? So for here, we have to have, it really is like, in order for the things to fuse, this deuterium and tritium, this hydrogen stuff, has to be like 100 times the density of lead in ambient conditions, and it has to have temperatures that are like basically in the many, many, many millions of kelvins. And so how would we even infer temperatures like that? How would we know whether we got it hot enough?
Comedians, any suggestions?
It's real hot in here.
It is.
Is that related to the question?
I don't know, but you can probably smell me sweating.
That's all I got. Are you guys warm? Yeah. It's a little
Yeah.
warm
So
for-
take off
It's
all
hard
your
for comedy
clothes.
when it's warm.
Let's see.
I am
Measure.
into that. I want to take my clothes off.
How do you think we can?
There we
measure-
go.
getting hot in here.
You want those backup dancers.
Do you mean
I get it.
Do you
I
mean
understand.
like that? How would we measure it? Because our devices wouldn't be able to survive inside of the heat
Exactly.
of the thing. Okay, we would do
Can we,
it.
can we just guess?
Psychically from inside of a tube that would be like in the E.T. movie.
We can't put a thermometer in there.
That's what we just
It
discussed.
doesn't have a bite.
That's what we just talked about.
What if it was a thermometer made of mystical material?
What if? Could
We're
you measure
just
the
eating it
stuff
up here.
coming off of it? Could you measure the particles that come off of
The
from
electromagnetic
far away?
radiation.
Ooh.
Actually, that is partially correct because people can do what are
Hey.
called
Thank
Oh,
you.
yeah.
Thank
See?
you. Thank you.
Yeah, you can.
We got a mic drop.
Thank you. There you go. It is good. Measure
Yeah.
her temperature.
There
Watch out.
are things called neutron time of flight measurements which actually do measure essentially how fast the neutrons are going, let's say, and that is certainly related to how hot the thing has gotten. These are the neutrons that are the products of the fusion events themselves. So that's one answer, yeah.
We had some answers out here.
Physics
jump out.
guy, you're not allowed.
Yeah.
Well, no,
Again.
I think.
Wait. Let's see.
The statute of
let's have
limitation.
over here on the right, because you haven't actually answered one of the official questions.
So kind of related to his answer, black body radiation. So you measure the light that comes out. And
Yes.
that'll-
Go to the
that
next
will-
slide.
Eureka!
Yeah. Basically,
nailed it.
Yeah, I mean, hot gas has a different, basically colors of light coming out or spectra than colder gas, and so because the electrons in the hotter stuff are more excited than in the colder stuff, and so when they de-excite, they give off different photons or particles of light. So that's right. That's what's another way, and that's one of the main ways. Yeah. But your way is also
It's
a
kind
way.
of the same as what I said, only not with light.
That's exactly right.
Kind of similar.
Yeah.
Sweet.
Yeah.
Awesome.
You're just as smart
What
as
were you
everyone
going to
else.
say? Because I'm sure it was also interesting. Okay, very good.
I got partial.
Yeah.
There's just no gifts left.
Oh, wait, there might be. Is there?
I think we have only
One more question. Are you guys ready for the
All right.
final question?
Woo!
Handle this? All right, here it comes.
So, okay, so let's say that we make this fusion stuff. And like I said, we're losers in the sense that we haven't done this, we haven't had gain in the sense that we have more power coming out than we've put into the lasers. So that's not cool. But we still make fusion events all the time. It's not like we can't do it. I mean, we're doing it. But what are the ways that this hot fusing stuff cools down after it's gotten to the point where it's gotten as hot as and dense as it's going to get?
You blow on it real hard? No. Okay. Like a big fan. Big fan. Nope. Okay. Anybody?
It does it on its own. That's a hint.
You can just let it sit.
So what did he say? Well, yeah, I mean, I'll give you certainly partial credit because you said entropy. I mean, and that's, well, so yeah, the fact that that's a thermodynamic concept. So yes, things are going to cool down naturally just because things are going to get more disordered. But yeah, well, I'm not referring here to how we would harness this energy. I'm just saying it's gotten really hot. What are the ways in which? So let me tell you what I'm getting at. That's not wrong, but what I'm getting at is that actually, the faster this stuff cools down, the less fusion we get. So we want it to stay hot pretty long. Now, of course, as you pointed out, this is some very small fraction of a second that it's at the states that it is in which the fusion is occurring. But I guess what I should have said, and I realize now I didn't express it in the question well enough, is what are the sort of enemies of fusion besides this leaking out thing that are making it so that it's not as hot as we would otherwise want it to be? In other words, the forces that are cooling it down.
Yeah.
And your thing is not wrong.
Like if it thinks about its grandma during sex?
Oh, Jesus.
Or like if it's on a windowsill. If you put it on a windowsill, like a cartoon pie.
You've lost your nucleus, Katie.
That's what they always tell me. I got
Throw it
it
over
right
here.
here. Oh, that guy.
Oh, look,
that was
yes.
mine, bro.
Yeah, you just got one.
Thanks.
Look at that.
No, it's all you. It's all you.
So let's find out with anybody else. No. Oh, we have one more.
Wait, do you want to answer a question? Yeah. Are you stretching?
Does it give off light or infrared radiation? Or?
So yes, that is absolutely one of the ways, and that is that it's in particular the
So,
electrons.
Eureka?
Yeah, sure.
Eureka! Ka-choo!
Any charged particles, when accelerated, radiate. And so the electrons, since they're going really, really fast once the thing is really hot, one of the ways in which you get something called, there's a German term, the translation is breaking radiation, but it's called Bremsstrahlung.
Bremsstrahlung.
That's also the name of the bench I got at IKEA.
So,
It's all the same.
She got to laugh. Let's not undercut her.
so when the stuff is really hot and it accelerates, then it gives off X-rays, in fact, and that's how so the electrons cool down through that. It also cools down just because, this baked Alaskan thing, the outer part is generally going to be cooler than the inner part, because the inner part's the part in the center of the big crunch. The outer part is the part that's expanding, right, the backside of the rocket, so it's generally a little bit cooler. And so it's just also going to cool, the hotter part is going to cool just through thermal conduction. You got a cold thing next to a hot thing, and so the heat is just leaking out kind of radially outward. And then the other thing is just the fact that the whole thing is expanding, which is why I'm giving you partial credit for the entropy, because that's related to the expansion. You heat something up, you can't keep something dense that's that hot. It goes, it's an explosion. So the thing is really exploding, and that's also cooling it because of this inverse relationship between temperature and volume.
1 second.
Pressure?
Yeah, I mean, it's relaxing to lower and lower pressures, thereby allowing it to get much cooler. So that's just naturally going to do that. So there's sort of three ways, what we call hydrodynamic, which is the motion of this fluid outward. That's one way it cools. Another one is Bremsstrahlung. and then the third way is just good old thermal conduction.
Cool, hold on.
Yeah.
So with these three as the barriers, how do you think it's possible to design the experiment so that it can sustain fusion? Or is this just a one-shot deal?
Well, it is a one-shot deal in the following sense. Nobody ever thought that this thing... So we are, in a sense, making a little star in the laboratory. That's actually literally what we're doing. It's very small. But nobody was ever thinking that the thing was going to be continuously burning like our sun is. It's not going to do that. Because exactly this business. I mean, the sun is kept in place because it's so much of it that it's the self-gravitating thing where it's all attracting itself just through its big mass. We don't have that luxury, obviously. So it's always going to be a very transitory thing. There's no way that we're going to have the fusion happening for a long time. It's just a matter of, the way that a fusion reactor would work to generate power, if we got to the point where we could do it, is we would be injecting pellets in like this a bunch of times a minute, and each time one gets injected, you get these pulses of these lasers, and then you get the neutron energy out, etc. And that's how the thing would work. But each one of these things would be of a discrete event.
All right.
We got one more, a final question of the night.
So if each discrete event fails to make more energy than you put into it, what is the logical leap that says that doing a lot of these things at once somehow would put out more energy than
it wouldn't. That's a good question. I mean, that's the whole point. We're not pursuing this sort of fusion energy engine, if you will, until we can show that we get a much bigger than break-even kind of a thing for one discrete event. So that has to be met before we try to, get cavalier enough to take it further.
And how close do you think we are?
I have no fucking clue.
To piggyback on that, so building the different kinds of machines, there's the magnetic fields, there's cylinder vacuums with magnets, and there's the electric fields, and then lasers. So there's all different kinds of ways to try for it. But even after we try for it, and we hopefully we can get the energy and money in to be less than the energy money out, so then it becomes cheaper than all of the other ones, because we also have to make it economically viable.
That's the part that's
cheaper than
bad.
Fossil fuels, cheaper than wind, cheaper than solar.
Whoops, I just stepped on my water. Yeah, so we're not that close to it yet, but the good news is that since this is a big mama honker laser, there's a whole bunch of other stuff that we've learned along the way to trying to do this. And so let me give you an example. Not that long ago, we compressed carbon in diamond form to like several times higher than the density of lead. And that's kind of interesting because then you can get to pressures that you have at the centers of giant planets. And as many of you probably have heard, there's been a revolution in planetary astronomy recently where people are now seeing extrasolar planets, right? People know.
Our show was about that.
Oh, good.
The Kepler mission scientist from
Very
NASA
good.
was here. Yeah, it was
so
great.
To understand the distribution of those different planets in the universe, you have to understand the relationship between their radii and their mass. Yes. Their mass-radius relationship, which maybe your person talked about.
Absolutely.
So that you can only understand if you know the equation of state of the constituents of the planet. and again, this relationship between pressure, temperature, and volume. And so we can measure that at this facility by whacking things and seeing, what their response is. So even shy of getting fusion, we can learn a whole bunch of stuff, and we are learning a whole bunch of stuff that is very relevant to people in that field.
And it was named after Johannes Kepler, similarly this was named after Coulomb, right? So the more that we go out and we do science, the more you can get cool shit named after you.
Very good. Everyone feel like they're an expert at nuclear fusion now?
Yeah! So
give it up here for Lorin, everybody. Woo! Yes. Now one quick thing. We did research on Lorin. We know that he's this amazing physicist, but he has other talents that he doesn't necessarily share with people. But we like maybe you do share, but not in this context.
Maybe he will.
Maybe you'll share with us.
Beatboxing.
Actually, that's fairly close. Lorin here scats. He's the scatting physicist.
Do we know what scatting is?
Not like the poop.
Yeah, not the poop.
Although I am sitting on a stool.
Oh.
Hey,
Look at this.
There it is. Solo
Give
show.
him.
So.
Would you do us the honor of demonstrating the scatting physicist?
A little short one.
Even though have the we've sing even you have the hood when wrong love the bobby visiting when even you have the written bend will belum ah.
Everybody. That was what I was hearing inside my head when you were talking about the equations. Yeah, that makes sense. Excellent, everyone.
Let's do one more thing before we close out. So we have these cool shirts that we just made. Before I talk about them, I do want to recognize someone special in our audience, and that somebody special is Lindsay Spurka. She has been a huge lover and of Eureka, and because of that, and sharing it with other people, and we appreciate her so much, and we would like to give her a gift.
Can I just say that I thought you were going to award the shirt to the person who was like the dopest in terms of answering questions, in which case I would have picked her.
Yeah.
Excellent.
So she has been compared to Hermione from Harry Potter because she comes and answers all of the questions. So we have a smarty pants on the back for her.
Give a big round of applause.
Yeah.
Here you are.
You are welcome.
Thank you.
And so one more quick follow-up about the shirts is that we last month, at the end of the month, Gala, as well as a few of our other brothers, came out to do a feed for people that are less fortunate than we are. For every t-shirt that you guys do purchase and rock for us, that we do go out and we feed people at the Civic Center and at the Tenderloin. And please hit us up. We aim to go out every month. We feed several hundred people, so if you'd love to come along for that journey as well, we'd love to have you.
Yes.
And
great. So give it up again for Lorin, everyone.
Thank you.
And give it up for our wonderful comedians.
Thank you, comedians.
Who helped interpret this. And to yourselves for coming out.
Thank you, guys.
Opening your mind.
And thanks for the listeners at home, too.
And next month.
Yes.
Well, actually later this month. October 30th, for the Bay Area Science Festival, we'll have Seth Shostak, Senior SETI Astronomer. So it's aliens, people. Aliens.
And there's different ways to discover life, and this one is listening for life. So please do mark it in your calendars. October 30th is going to be a Sunday at 7. Bring friends, tell friends about it. Thank you to you guys at home for listening. We much appreciate you. Keep tuning in.
And
thank you
guys. And have a wonderful, wonderful night. Thank you for coming out.
Thank you.
Woo! Great job.